Today's lesson is a continuation of section 8.1, apply exponent properties involving products. The other day we learned, or the previous lesson, and it says Friday, but not necessarily Friday for us, but the previous lesson, we learned two different rules, how we can simplify problems that involve powers, and especially if they had the same, like for the first rule, if they had the same base, if two powers had the same base, then what I could do is, remember this is kind of like 11 different 4s multiplied together. And this one is like 12 different 4s multiplied together. And then if I multiply those, what it's really like doing is multiplying 23 different 4s together. So really I can just add those two exponents and say this is 4 to the 23rd. And that's a nice rule I can use to kind of shortcut to the answer. This second one, we also kind of showed something like this, a power to a power rule. If I have x to the 5th power and that to the 9th power, what that means is I'm taking x to the 5th and multiplying that by itself 9 different times. And if I broke all those x's down, then those would all be 5 x's multiplied times themselves, and then 9 different sets of that. So it's just like multiplying these two numbers together, and that's how many x's would be multiplied together altogether. It'd be 45 of them. So this is really just like x to the 45th. I can just multiply those two exponents together. So we learned these two rules in the previous lesson, and now we're going to kind of move on and learn a new rule today. I'm going to show it using this first example here. And as I usually tell students for this first example, what would you probably do in this problem? If I just showed you this problem right now, what would you probably do? Many students say, well, I know what 2 times 3 is, or 3 times 2, and I can multiply those two numbers together and get 6. And then this exponent just means I'd have to square whatever that answer is, so 6 squared would be 36. And I always agree with them. I'm saying that's what you should do. I'm using this problem, though, to show why the rule that we're about to learn works, though. And what it is whenever I'm multiplying two numbers, or a variable and a number, or two variables, whenever I'm multiplying some things together inside of parentheses, there's a rule that says I could also do it this way. If I have 3 times 2 and that's squared, we can do it the way we set up here, or the way we kind of showed first originally. I can multiply those numbers together and square it. Or there's a rule that also says I can actually just take each of these things separately and apply this second power to it. And I often tell the students, it's kind of like if it helps them, they can think about distributing, kind of like distributing that 2 to both the terms inside, kind of like when you have 2 times 4x plus 8, like we did earlier this year. They can think about that. It's really not the correct term for what we're doing, and I do know that it's not the correct term for it. But some students, it kind of helps to think about that, like, oh, okay, I'm going to just make sure I apply it to each thing in the parentheses, because with distributing, we often said, oh, you got to multiply this number to each thing in the parentheses as well. So some students, that helps them a little bit, but really what you're doing is applying this power. I'm going to apply the squared power to each of those numbers. Well, then what I get is I get 3 squared times 2 squared. And 3 squared, well, that's just 9. 2 squared is 4. And if I multiply those together, what does it equal? What do you know? It equals 36. So that's why I just kind of shown here to start off with this example. You know, the numbers are smaller, and you could probably figure out the answer almost in your head. I'm showing actually with this second one, here's the rule that we're going to talk about today. If I have things multiplied together in parentheses, and it's to a power, I can just take that power separately to each of those things, whether it's numbers, variables, no matter what. And notice it would give me the exact same answer. So again, going on to the next page here, this was that first problem. What I would ask students to do in something like this is it says simplify. It doesn't say evaluate. I don't have to find the answer. It just wants them to use this exponent rule. So they could say 3 squared times 2 squared, just like we did there. Okay. Same thing with this one. 4 times 3 to the power of 2, or squared. So again, it's kind of like, I mean, sometimes I'll say distribute, even though I know that's not the correct word, but sometimes it helps students think about what we're trying to do. Is I'm going to take that 2 power and distribute it to each of those numbers in there. Or again, what I should really say is apply that power to each of those numbers in there. So this would be like 4 squared times 3 squared. Again, with numbers like these, students probably would just usually figure out the answers. Sometimes the book will give them a few problems like this, though, where it's like 25 and 46. So these numbers, obviously not ones they'd probably be able to do in their head, or ones they could even figure out with a calculator, but this is the one that really kind of shows, okay, do they know how to use the rule? what I would do is just take that 7th power and apply it to each of those numbers. So 25 to the 7th times 46 to the 7th. So here's the rule though. The basic rule itself, it's a power of, and actually there should be a little a in there. I kind of forgot to add that, power of a product. When I have the power of a product, and again, all those words are saying don't be too fooled by the word. It's a power. Okay, when I have something to an exponent of a product, so it's things that I'm multiplying together. Things that I'm multiplying together, that's to a power. Okay, which is exactly what this example is showing, and exactly what the ones up here are showing. But what happens in those cases? Well, as it says right here, if I have m times n to the b power, really what I can also think of is the same thing, is if I just take that whatever that b power is, that number, and just apply it to both of those numbers. And that works. Just like I showed with the examples above. And again, just kind of showing one more of those. 42 times 73, both these they're multiplied together, and they're both, all this is to the 11th power. So one way you could do it is you could just multiply these numbers together and then take that to the 11th power, whatever that answer is. But again, the rule they're trying to show you, I want you to understand, is I can actually just apply each one separately to the 11th power. So it's really just like 42 to the 11th power times, 73 to the 11th power. Okay. And again, those are big numbers. I'm not concerned whether students know what those big numbers are. I just want them to be able to execute the rule properly. So that's all they have to write. Here's where more we're going to use it, is in a problem where we have variables, or numbers and variables. Similar thing with this one. This is x and y. Remember, each of those variables stands for a different number. And really, when the x and the y are right next to each other, it means that they're really multiplied together. So really, this problem is just like the one above. X stands for a number, it could be like 42. Y stands for a number, it could be something like 73. So what am I going to do is I'm going to take the 5th power to each of those, apply that exponent to each of those variables, and what do I get? I would actually get x to the 5th times y to the 5th. And again, just by writing them next to each other, that just means they're multiplied together. So if it helps, you can put the multiplication sign up there if you like, but you really don't need it in this case. This one, very similar idea. Again, just like the one above, I'm going to take this 5th power and apply it to each of the variables in here. But just notice in this case, right here I have y to the 3rd, and that's to the, y to the 3rd power. So it looks a lot like the problem above. This problem looks a lot like the problem above, but the y now has a power. It has to the 3rd power. Well, remember the rule we learned from yesterday. If I have a power to a power, then what happens? I just multiply those two numbers together. So this one starts off like the one right above it. X to the 5th power would just be x to the 5th. But then y to the 3rd to the 5th power, I'd actually multiply these two exponents together, and I'm going to get y to the 15th. Again, each of these rules, and I'm going to show this, in this chapter, chapter 8, none of the rules standing by themselves is too tricky to understand. But when you have problems like this, or like the ones we'll talk about, where all of a sudden you have to start combining some of them, okay? Even that's not super tricky, but it is just a step up. It's something you have to be able to do in terms of steps, just like I think I talked about in the last lesson, how we solved multi-step equations in chapter 3. And some of those problems took 5 steps, 6 steps. Same thing with problems like these. Some of the problems will take a few steps, kind of like I have to do this first and then this, and then I can finally get to my answer. And I just have to be able to kind of apply the rules as I go. Similar problem like this, and like ones we'll do, just each rule, if I just kind of take my time and go through the problem step by step, I can still get to the right answers. Okay. I'll look at these two together. They're kind of similar. Like the one above here. Again, this one's got two things multiplied together in parentheses, but in this case it's a number and a variable. So 3y squared. Well, again, this is to a power. So what I'm going to do is I'm going to apply this 3rd power to each of these things, to the number and to the variable right here. Well, when I apply the 3rd power to the 3, that just ends up being 3 to the 3rd. Y squared to the 3rd power, that's a power to a power. I'm going to multiply those together and get y to the 6th power. And that's the simplified version of that one. I just apply it to each thing, even if it's a number, if it's a variable. just like that one, I had 3 to the third power. That's totally fine. Okay, that's the way I can write that. We can even figure out what 3 to the third power is. I'll talk about that in 1 second. But I just apply that third power to each of the things that are multiplied together in the parentheses. Same thing with this next one. This whatever's in parentheses here, it's 2 times x to the 6th. That's to the 4th power. These things are really multiplied together. So what I can do is I can just apply each one separately to the 4th power. 2 to the 4th power, which is what I'll write, and then x to the 6th power. And if I take that to the 4th power, again, that's a power to a power. So I'm just going to multiply those two exponents together. So I'll get x to the 24th. There's the way I can write both of those answers. One more thing I'll say about these two problems, these last two, is when you see numbers like this, like 3 to the 3rd, or 2 to the 4th, or just say you had something like 8 squared x to the 5th, ones like these that you can figure out pretty well in your head, or that are, not something in the hundreds or thousands, then those I would like you to actually put in the answer. 3 to the 3rd just means 3 times 3 times 3. 3 times 3 is 9, times 3 one more time is 27. So this is just 27 y to the 6th. So I'd rather you write that as the answer. When you see a power that you can evaluate pretty quickly, even in your head, or just with some smaller numbers like that. 2 to the 4th is just 2 times itself 4 different times. 2 times 2 is 4, times 2 again is 8, times 2 is 16. 16x to the 24th. That's what I'd rather you put for one of those. X, or 8x squared. 8x, or sorry, not 8x squared, 8 squared x to the 5th. 8 squared is 64. Again, one that students have known now for a long time. So you just put 64, x to the 5th. If the problem is something like 11 to the 21st power, okay, then no, I just want you to leave the answer like that. But all these other cases up here, again, these are all ones that students I would figure can almost kind of do in their head, or pretty quickly. So those I would like you to put in the answer when you run into a case like that. Showing just a few more examples here, and also something else we can do with some of these problems. And again, also just showing how, again, they kind of build on each other like the equations did, where I had multi-steps. I do one step first, then I do another, then I do another, and then I can get to my answer. Looking at this first one here, it says simplify. So I'm going to simplify using some of the rules that we've learned so far. X to the 6th, in parentheses, to the 4th power. So that's a power to a power, times x to the 10th. Well, with this first one here, what I can do, this stuff in parentheses, and it's kind of like PEMDAS, where often these problems you'll look to do something with parentheses first if you can. X to the 6th to the 4th power, I can just multiply those together. That's a power to a power. That's going to give me x to the 24th. So then I've kind of simplified that part. And now look, if I have x to the 24th times x to the 10th, that was like the first row we learned. That's like 24 x's multiplied all together, times 10 more x's multiplied all together. That's like 34 x's multiplied all together. So I just add those two, x to the 34th. So again, notice there was a couple steps there, but just using our rules, and do a step by a time, we can get to the answer. This one as well. Again, here's a parenthesis, so usually I'm going to start with something like that. And again, I tell students too, as they're doing these problems, they start to get, a little tricky, because there are a few steps. And it's not that, as I go through them here on the board, it's not that I am even that much better at them than them, or that much smarter. I've just been doing these problems for so many years that I know kind of where to start, as they practice them too. It's just like shooting free throws or anything you might do in sports. The more you do them, the better you get them, the more you start to see, where do I have to start and what's my next step. So it just kind of takes practice. And sometimes it gets a little frustrating. I know students get a little frustrated during this section, but as they go on, they get a little better at it. So just kind of keep encouraging you to keep moving as you're doing the problems. So you will get better at them, keep trying them, and we can always talk about them more in class. This one right here. Again, usually if I have something with parentheses, I probably will start with that. 3x to the 9th squared. So again, what I can do is I can apply that squared power to each of those things. 3 squared gives me 9, so I'm just going to write that right away. X to the 9th squared, I can multiply those together and get x to the 18th. And then that times 5. And remember this from way back in chapter 2. If I have numbers here multiplied, all this is multiplied together, 9 times x to the 18th times 5. I can actually just multiply the two numbers together. And what I'll actually get is 45 x to the 18th. If I just see two numbers like that, I can multiply those together and keep moving. One more example to go through here. Again, in parentheses, I can deal with this part first and apply the second power to each of those. So I'll have 7x to the fourth times, well, 3 squared will be 9. X to the negative third time, to the second power is where I multiply them, and I get x to the negative sixth. And here again, I can multiply these numbers together and get 63, and then apply my exponent rules here, x to the fourth times x to the negative sixth. I add those together and get x to the negative 2. So again, we'll notice that we're kind of using a couple of different rules, but if we just kind of take our time and step through them, we can do that effectively too and still get to the correct answer. So.